project consisted in the design and manufacture of our composite material with a reinforced matrix, fibers, particles, powders, or laminated composite. Our main objectives were focused on creating a composite with degradable materials, hardness, and a high elastic modulus. After doing an extensive research, we chose to use three different types of matrix, was the same for the three composites. We considered the proportion 60% matrix and 40% reinforcement.
All of our composites have bamboo fiber as the reinforcement. The first matrix is a biodegradable polymer made of flour and water. The second matrix is a polyurethane polymer, and the third one is an epoxy resin. The process of manufacture consists of three phases: the extraction of the fibers, the matrix preparation, and finally, the cast and adjusting to the mold. The first step of our process was extracting the bamboo fibers, first by soaking them in water, then retrieving the fibers from the stem, and after that, we let them dry, and finally cutting them 100 millimeters long to fit the mold for the test tubes. The second step was preparing our matrix for biodegradable one. It's a mixture of flour and water and then cooked. Then, for the epoxy resin matrix, we mix 1 part of resin and 1 part of catalyst, and the polyurethane polymer was ready to use. As we consider the proportion of 60% matrix and 40% reinforcement, we elaborated two molds. The first one to get the desired dimension for the test tubes, and the second was to get the correct proportion of the fibers. Then we filled the mold and let it dry. Also for the fish composite, the biodegradable one, we sprayed a coat of plastic lacquer.
The first is deflection test. We decided to add different loads attached to our test tubes in a bucket until the material eventually failed. The impact test, we dropped the test tubes from 3 different heights and we looked for fractures each time the test tube fell. We repeated the test after putting 8 hours in the freezer, the test tube. In the flammability test, we placed the test tube in contact with the flame for 30 seconds. For the biodegradable test, we buried the test tube and 1 week later we dig them up and observe the changes. For the sun exposure test, we placed the test tube 5 hours to the sun.
The results of our test are resumed in this comparative table and fill it with the properties of each composite we obtained. In the flammability property, we found that the most flammable one was the second composite. In the biodegradability, the most degradable was composite number 1. In water absorption, the second composite has the lowest percentage of absorption. The most brittle composite at room temperature was the first composite and also the most brittle at low temperature. The highest of the maximum stress was the third composite. We obtained this value with the bending test, knowing the maximum load applied at the moment of the fracture and the cross-sectional area of the test tube. The second composite presented high ductility and was the most resistant to UV rays. We determined this with the sun exposure test.
The most alike material that we found to the bamboo polyurethane polymer is rubber, because they share many characteristics as waterproof, the impact absorbing properties, and it's flammable. We decided to choose composite 2 because we found its properties very useful in nautical applications. Usually any type of boats use buoys for parking. These buoys do not need very large forces because the boats are tight, and the property that most interests us is the ductility of the composite. Also, the composite had zero absorption, and we could see that when it's exposed to the sun, nothing happens, and we also know when the weather is cold, the material won't fail.
A composite is a material made up by a matrix which binds, gives shape, surface quality, and load distribution, and a reinforcement which provides strength and stiffness. Let's take a look at 3 food waste that could actually become reinforcements for composite materials. Crab. It contains chitin, calcium carbonate, and protein, which provide high strength, lightness, flexibility, and mechanical rigidity. Clamshells. The abundant calcium carbonate, plus the calcite and aragonite offer high compressive strength, thermal stability, and high toughness. Coconut shell. This material possesses low density, great strength, and modulus properties. The chosen matrix is epoxy resin due to its strength and resistance to corrosion, cracking, moisture, impact, and peeling. A particle composite material was chosen due to the ease of production and the gained stiffness, strength, and toughness with an isotropic configuration. Now, let's talk about the followed manufacturing process. The clam shells were washed and cleaned, dried for 6 hours, grouped and smashed with a hammer in a cloth, grinded up with a mortar and finally strained. The crab shells were deeply washed and cleaned with chlorine, dried for 48 hours, grinded up with a mortar and strained. Coconut skin. The fruit was removed, the skin was dried for 24 hours, smashed in a cloth, grinded up in a mortar, milled and strained. The sample tubes were made with a proportion of volume of 86% polymer matrix, 14% particle reinforcement. Each test tube has a total volume of 70 milliliters. Firstly, 10 milliliters of particles, 30 milliliters of resin, and 30 milliliters of catalyst were measured. Then, the three components were poured into a container and mixed for about an hour. After it, the mix was poured into a mold and bubble spray was applied to it. Afterwards, it was left to dry for 24 hours. Finally, the sample tube's excess was cut and sanded. In order to test the new materials, 6 different tests were designed and developed. Impact test at room temperature. Each test tube was dropped in free fall from a height of 7 meters, landing on a plain concrete surface. The drops were repeated until major fractures appeared or the limit of 70 drops was reached. Even though the pure resin had greater impact energy, it could withstand more cycles than the composites. The composites had brittle fractures at the center. Impact test at -18°C. The same impact test was repeated with test tubes previously exposed for 12 hours in the freezer. All the test tubes experienced greater resistance to impact under this condition. However, the pure resin was still better than the composites. The coconut reached the maximum of drops, but it had more damage than the pure resin. Flexural test. The test tube was placed on a wooden support, leaving a distance of 8 millimeters between each end and the supporting points. A rope was tied to the sample and placed at the center of it. All the loads were measured with a scale. During the test, the loads were gradually applied until the sample tube was fractured or the limit of 250 kilograms was reached. According to the flexural modulus and deflection obtained, it is possible to conclude that the pure epoxy resin was the one which opposed more to deflection. The second best material was the crab composite, and the worst was the coconut. Hardness test. The test tube was rubbed back and forward 50 times with a basalt tegelode, steel scissors, stainless steel knife, and an aluminum key on each face of the sample. The surface's damage was the comparison point. After a visual comparison, the crab composite was the material which could better withstand the rubbering. The worst one was the pure resin. Water absorption test. The sample tube's mass was first measured on a scale, then placed on a closed water-filled container at room temperature. The mass was measured every 24 hours for 7 days, and without doubt, none of the materials absorbed water. Density test. The test tube's mass was measured on a scale. Then, the test tube was placed on a container with 500 milliliters of water. After it, the differential volume was measured with a syringe. And finally, density was calculated with mass and volume. The most dense material was the pure epoxy resin. The composites had a lower mass-volume ratio, being the clam composite the lightest of